Hello everyone, my name is Arundhati Sharma and today I will be presenting my work on calculating path loss using the Okumura outdoor propagation model. This research is conducted under the guidance of Dr. Bharatish A. Let us begin by understanding the motivation and significance of the study. The Okumura path loss model is an empirical radio propagation model that predicts the signal attenuation for mobile communication in various terrains. Developed on real-world measurements in Tokyo, Japan, this model is widely used for frequencies ranging from 150 MHz to 1920 MHz and distances from 1 km to 100 kilometers. This model helps network planners optimize base station placement and coverage estimation. So the objective of this project is to simulate the Okumura model using MATLAB and to provide useful graphs to draw conclusions from using MINITAB. We aim to analyze how different parameters such as distance, frequency, and terrain affect the path loss. Our goal is to generate meaningful plots that help us understanding median path loss behavior. Here in this image, we can see the general flowchart of how the path loss determination model works. You take the measurement and the path loss model is done. Optimization process to perfect the path loss model of the data sets. We validate the data sets and then the statistical analysis is performed and then the development of the optimized path loss model is taken underway. This section, the literature review, reviews the existing research on path loss models, including alternative models like HATA and COS 231. It highlights why Okumura's model is still relevant despite the newer models. We also explore the use of artificial neural networks (ANN) to predict the path loss. The main journal in focus over here is Elsevier, which makes use of the Okumura model in various different terrains and like locations. The first one being the use of the comparative assessment data obtained using empirical models for path loss predictions in a university campus environment. This was like a relatively small but a detailed model that was made, and on similar lines there were two other models made on a larger scale. One was in Nigeria, which was for the determination of path loss and modeling for digital terrestrial television signals, and the other one was for a wireless communication for 4G network, which was specifically tailored for Muscat's urban environment. A review for the radio wave propagation model for very high frequency and ultra high frequency band also undertakes. The model relies heavily on graphical data, which offers quick reference loss under various conditions. It is less precise in rural areas without applying the proper correction gain factor. The literature survey also consists of the regression model for missing data for Oman. And so basically, from available papers, it can be assumed clearly that the Okumura path loss model is practically based on how it was applied and developed in Japan and how it can be placed in other countries or regions, whether it's as small as a university campus to as big as a city or another country as a whole, and then at the same time be implemented or superimposed over there. Moving forward, so we have the path loss in Okumura model. The general formula is given there. It is based on empirical data rather than on theoretical equations. It considers environmental factors like urban density, obstacles, and antenna heights. The model is widely used for cellular network planning. Here we see that the main focus of finding here is the variables that we are looking for is the path loss and the free space loss, while the factors which were considered in the formula are the median attenuation obtained from the imperial data or Okumura graphs, the gain due to transmitter antenna height, the gain due to receiver antenna height, and the gain based on the terrain, that is, it is urban, suburban, or rural. ANN or artificial neural network is a computational model inspired by the way human brain processes information. It is basically machine learning can improve path loss prediction by learning from data sets instead of relying solely on empirical formulas. ANN-based models adjust based on observed patterns in the real-world data. They are designed to recognize patterns, classify data, and make predictions. So the first step for the ANN model is dataset preparation. We give the input features such as distance, frequency, transmitter height, receiver height, or terrain type. Urban, suburban, and rural are the three things that we are considering over here. And then the target variable being path loss values from the Okumura model. The second step is the ANN model architecture. So for the ANN model, what we have is the ANN model works in form of layers. The layers are going for the input layers require us to give the variables or the factors that we are considering. In our case, we are considering the 5 input features mentioned before. The hidden layers, then there are something what is called, we call as a hidden layer. So the ANN model works in the form of neurons. There are neurons in every layer. We can correlate this with the use of like photo pixels in a photograph. So we all know when we are looking for a good quality camera, we are looking for a high pixel quality camera. Better the pixel rate, better will be the quality of the photo. Similarly, the greater the number of neurons used in each layer, like 64 or 128, a better refined and a more clear model would be developed for future predictions. While the output layer is a single neuron to predict the output, it is a regression task, so there is no activation or linear activation function. So the hidden layers also make use of rectified linear unit, which is an activation for non-linearity. It in this case it helps in complex data sets that can be compiled together. The step 3 is training. Training the ANN model on the dataset by minimizing the mean squared error or the mean absolute error loss function. We'll talk about this in more detail further on. Using the gradient descent based optimizer like Adam. So the data set which is developed by minimizing the mean squared error and the average error. So we split the data set into 3 types. The training, the one data set that has been incorporated into the code by us is used to train the model. There's a certain restriction over here which you need to focus on, is that the data set needs to be big enough to validate the model and to produce further future predictions. Validation, a part of the data set is used to validate the trained data set. They are both plotted on a graph and superimposed on each other, so that the validation and the trained data set need to have a certain linearity and a similarity when they're being plotted. And then future predictions are made, and then these data sets are used as test sets or for future uh, conclusions that can be drawn from them. Test sets can be of any number. It can be, since here we are taking 1,000 test sets as the bare minimum, as the whole data set value. And then lastly we go towards implementation. So parameters, the key parameters influencing path loss include distance between the base station and the receiver, frequency of transmission, transmitter and receiver heights, terrain type, urban, suburban, and rural. So the dimensions or the range of each of these data sets has been mentioned, and the frequency range, of course, we are taking from 800 to 2600 megahertz. These data sets are inputted into the ANN model, which then produces a random variation of all of these fit together, and then produces some 1,000 data sets altogether. The responses to be measured. The primary responses measured are path loss. It is the reduction in power density of a radio signal as it propagates through space. This can be influenced by distance, frequency, obstacles such as buildings or mountains, or how much the signal is being lost, or how much is it being reflected back, depending on the environment it is in. Correction gain, which adjusts for antenna heights. It accounts for the gain effects of the transmitter height and the receiver height. And then factor gain. Factor gain represents the effect of the frequency and the terrain type on the signal. So the terrain factor represents signal propagation behavior in different environments. The factors that correlate with the different terrains, urban 1, suburban 0.8 and rural 0.6, have been mentioned already in the Okumura model, and these are predetermined based on the measurements taken before in Japan. So dataset creation. The dataset is created using Python and simulated for real-world conditions. We make use of libraries such as matplotlib, which is from MATLAB, and from NumPy and Pandas. So random values are generated for distance, frequency, transmitter height, receiver height, and terrain type. The path loss is then computed using the Okumura equation. So NumPy is used for numerical operations like logarithmic calculations, and then Panda is used to create and manage these structured data like tables and CSV files. The CSV files are important because these would become the basis of the data set file, which would then be transferred to MINITAB, where it can be plotted into useful graphs so that a decent conclusion can be drawn from the entire setup. Secondly, we go towards the generate key features. This is where we give the range of the values and the frequent and the distance it should be an over period of what it can be on. So distance, it affects the path loss due to signal attenuation over long distances. As you can see, it has been taken from 0.1 to 20 kilometers. Frequency impacts the signal penetration and reflection. High frequencies suffer greater losses. Frequency that we are considering is between 800 MHz to 2600 MHz. Transmitter and receiver heights influence signal reach and strength. So the transmitter height has been taken between 300 and 200 meters, since it is generally considered in general cases that a transmitter height from any company would be a taller tower, and the receiver height is between 1 and 20 meters. It can be any residential building or even commercial buildings like the small ones in a an urban and suburban area. Terrain type which we have taken is urban, suburban and rural, and we have given them a set of values 0, 1 and 2 for the code. Step 3 is to compute the path loss using the Okumura model. The artificial neural network is designed to predict the path loss based on 5 input features. As we've already mentioned, it has multiple layers of ReLU activation, allowing it to capture complex relationships. The model is trained using the ADAM optimizer to minimize the mean squared error. The terrain loss, we considering that the urban has 0 decibel loss since dense buildings scatter the signals but can provide reflections. Suburban areas have 5 decibels of loss considering that moderate obstructions like trees and smaller buildings. And rural areas have 10 decibels of loss. Open areas with fewer obstacles but longer distances can cause higher deviation. So the Okumura path loss model has different values, formula has different factors or parts. So there's a loss due to increasing distance. The higher frequencies suffer more attenuation. There's a 32.44 constant for the standard free space path loss. And then there's the terrain height and receiver height, which improve the reception. The data set once is developed is split into two, train and test on both X and Y. And the data set is for easier processing and faster training. As we've already mentioned, there are three kinds. It is developed for training and then for validation and then test sets. Defining the ANN model here. The ANN is trained over 50 epochs with a batch size of 32. Now, what do we mean by epochs? So epochs are basically the number of time a particular data set will run. The data set considering of a batch size of 32. Now each batch of 32 will run through a set of neurons or through a set of layers. Each layer has a set of neurons. The neurons that we have taken as 64 in the first layer, 128 in the second layer, again 64 in the third layer, and then the final output layer has a single neuron for a single path loss calculation. So this entire process of 64, 128 and 64, again 1 and output, goes through this batch of 32, goes through this 50 times. So we compile the model. The model is expected for 5 input features and 64 neurons in the first head inlet. The rectified linear unit activation function is used to introduce non-linearity, allowing the model to capture complex relationships. 128 neurons provide a higher capacity for learning complex patterns. ReLU is used to avoid the vanishing gradient and improve training efficiency. Considering the fact that a data set, if it is not enough to train the if the amount of data accumulated is not enough to train the model so that it can make future predictions, then there will be a certain issue when as the model is being trained and predicting. What we come to this conclusion is called the vanishing gradient problem, that suddenly there's a halt in the data and then the data takes an abrupt turn rather than following a linear or like a normal curve path. So for proper optimization of the dataset, we use the ADAM optimizer. It works well with noisy data and large datasets and requires minimum hyperparameter tuning. It adjusts learning rates dynamically to improve the training. For going forward, we also have the mean squared error, which we were talking about previously. It is used for regression tasks. It penalizes larger errors more heavily, helping the model to make accurate predictions. And then the evaluation metric, which is the mean absolute error. It is the average. In simple terms, it is the average absolute error between predicted and actual values. It gives a better sense of real world prediction accuracy. If the error is 2 decibel, the model is then off by 2 decibel on average. Whether the model might be off by 12 decibel at some point and then by just uh, 10 decibel and then again 2 decibel, the average of entire thing would come down to 2 decibels. So on average the model is off by 2 decibel. That is how we get a proper verification of the model of how worthy it is of being put forward for making for future predictions. So we train the model and fit the exchange by specifying the batch size, the epochs, and the validation of the data set is in the X model, and then evaluate the model. Then again, this evaluating is basically the training and the validation loss. The training loss and the validation loss are the two trained sets, and the validation sets are then superimposed on each other on a graph and then seen for the variation in both of these data sets. If the trained data set follows the same path as the validation data set, then we can say that the trained data set is worthy of moving forward and finding out that and getting converted to the test data set, which can further make predictions by making a larger data set for various regions and from as small as a school or a college to as big as a country. We compute the correction gain and compute the factor gain. Now here, since we have calculated the path loss, we need to add on to with the correction gain and the factor gain. So correction gain, as we already mentioned, accounts for antenna heights. Higher the antenna reduces signal obstruction, improving reception. A logarithmic scale is used to represent this diminishing effect. While factor gain adjusts for terrain and frequency interactions. Urban areas assume minimal loss, while suburban and rural areas experience greater attenuation. So we store the dataset in a pandas data frame. The dataset is extended with these new parameters of correction gain and factor gain, and to analyze and visualize how different gains influence the signal strength. They are saved in CSV format, which makes it easy to use the dataset for analysis in tools like Python, Excel, or MATLAB. Here, in in this case, we are going towards the use of MINITAB. MINITAB is a much better format to use in case for this function because it has a very user-friendly interface as well as a general idea of how it can be plotted through various formats. The most common ones are just mentioned in this slide, which was Python, Excel, and MATLAB. Going forward, I'll explain how the MINITAB works in a much better frame. So, MINITAB. So, it is a powerful statistical analysis tool used for data analysis and visualization. It is widely used in academia, research, and industries such as manufacturing, healthcare, finance, and engineering. All these industries are more towards making the process efficient and uh, less time utilizing and better for the return on investment. So it helps the users explore data sets with descriptive statistics, graphs, and summary reports. Common visualization includes scatter plots, histograms, box plots, and control charts. So for going forward, what I have used is a scatter plot with a regression line, which draws on the basically the best fitting line of the entire data set. Considering that the data set consists of 10,000 random data that has been generated, it helps in identifying the patterns and trends in the relationships in the data with the regression line. So the linear and the multiple regression analysis to predict future outcomes based on past data. It helps in modeling relationship between the dependent and the independent variables and supports logistic regressions for classification problems. So the MINITAB plot. So the first and the most important plot that we are looking for is the scatter plot of a path loss versus the varying distances there's between the receiver and the transmitter height. So the scatter plot shows the path loss increasing with distance. The red trend line indicates a positive correlation between path loss and distance. So path loss is low around 40 to 60 decibel and signal experiences less attenuation, but it rises steadily, and free space loss and environmental obstructions, the signal weakens because of these. So path loss grows logarithmically with distance. For network optimization, increasing the antenna height can reduce the path loss. At greater distances, signal attenuation becomes more significant. So signal boosters may be needed for long distance communication. Also, I would like to mention that the data set for all of these MINITAB plots has been put into the description below and the code as well. So the path loss versus path loss versus transmitter height. Higher transmitter height reduces path loss because signal travels farther with fewer obstructions. The weak trend suggests that the other factors, distance, frequency, terrain, dominate the path loss impact. Increasing the receiver height for path loss versus receiver height. Increasing the receiver height, of course, improves reception by reducing obstacles, example buildings and trees. So path loss decreases as the receiver moves above obstructions. However, the impact is limited at higher distances, explaining weak correlation. Path loss versus frequency. Higher frequencies experience greater path loss due to higher attenuation in free space. This confirms that lower frequency signals, example around 800 MHz, propagate better than the ones around 2600 MHz. So, MINITAB plots for correction gain and factor gain versus path loss. There is a negative correlation between correction gain and path loss. This suggests that higher the path loss condition require less correction, likely due to environmental or propagation factor. The scatter shows some variation, but the overall trend is clear, which is towards the downward direction. While the factor gain shows a positive correlation with path loss. This indicates that higher the path loss conditions require greater factor adjustments. The variation is more scattered but still follows an upward trend. The Okumura model is effective for predicting path loss in outdoor environments. ANN can further enhance the predictions by learning from empirical data. MINITAB visualizations help validate our results in the same scenario. So I would like to thank you all for watching this video and for taking your time. I'm happy to take any questions and looking forward for any good constructive criticism. Thank you.